Alright, so now that we've talked about the determinant a bit and did some computations with it, and we talked about some of the properties and implications that it has, we want to talk a bit more about it. Ultimately, we want to summarize sort of, you know, all these properties that a matrix has, related to it being invertible. And we've done a good deal of them, but we really need to know some more about the determinant before we can quite get to that. So, what I want to talk about here is one of the most important properties that a determinant has. All right, so let's start by multiplying these two matrices, A and B here. All right, so this is going to be 6 plus 20, so that's 26. Let's see, this one will be negative 3. All right, down here we got 8 plus 15, that's 23. And down here we get negative 4. Okay. So let's find the determinants of all these things. Okay, so the determinant of A, this is going to be 9 minus 16, which is negative 7. Right. Determinant of B is going to be 0 minus negative 5, so that's 5. All right. Now let's do the determinant of A times B. But before we actually compute it, and without doing the numerics in your head, what do you think it might be? See if you can make a guess first. So pause it here if you need to. All right, let's actually compute it. So 26 times negative 4 is negative 104. And then minus 23 times negative 3 is negative 69. All right, so that's negative 104 plus 69. And that will be negative 35. So was your guess correct? If you look at what we have here, we have that the determinant of A times B is equal to determinant of A, determinant of B. Right? And that's quite a crucial property for determinants there. All right? So let me summarize that as a theorem. Okay? So here, A and B, we need these to be square matrices. Okay? Then, the determinant of A times B is equal to determinant of A, determinant of B. Right? This is one of the most important properties that determinants have. So I'll let you look at the book as to why this should be true. But basically it's going to come down to kind of looking at elementary matrices. So I'll let you read that over. So, what's some consequences of just this definition as is? Well, something we might call a corollary, let's say. Right? Corollary in math, or really in anything, just a corollary of something is a fact that follows immediately. Right? So from this fact, we get another fact for free, basically. So I'm going to write this as if A1, A2, AN, if these are square matrices, right, then I'm going to use the other determinant notation just because it'll make this shorter. The determinant of A1 times A2 times AN The determinant of a big product of matrices is just the product of the individual determinants. Right? So if we can break up the product of two things, we can break up the product of, well, as many things as we need to. Right? That's just a direct corollary. Now, another theorem I want you to think about, and this is really in a way just another corollary, but I'll write it down as a theorem. Right? So here again, A, this I need to specify as an n by n matrix. Okay? And C is just, well, any real number, really. Right? So this notation here, we've talked about it before, but this just means C is an element of the real numbers. So it's just shorthand for saying C is a real number. Right? So if we have an n by n matrix and C is a real number, then the determinant of C times A, how do you think this relates to the determinant of A itself? How do you think that relates? Right. So think about row operations, right? How did row operations affect the determinant? Well, if you take a row, a single row of a matrix, and multiply it by a constant, then it multiplies the determinant by that same constant, right? So if that's the case, and here we have every single row multiplied by this constant C, then we get a copy of C for each of those rows, right? And there's n total rows, so this would be C to the n. Right? It's pretty interesting how that works out. And, we've kind of mentioned this, when we're doing determinants, that you can factor a constant out of a row, but we can factor a constant out of the whole matrix and just get, this C to the n, and maybe simplify the determinant a bit. All right? So we have those nice facts. But there's one more really nice fact that I want to end this particular video with. And that is, question, what is the determinant of A inverse? Okay. So here, by writing down A inverse, we're assuming A has an inverse. What I want to ask is, how does the determinant of A inverse relate to the original determinant of A? Right? How does that work? Well, let's think about this. We know that A times A inverse equals the identity, right? So we can take the determinant of both sides. Okay? But we just talked about, here we have a product, we just talked about how the determinant of a product relates to the individual ones. So, this is determinant of A, determinant of A inverse. What's the determinant of the identity matrix? What do you think? It's a diagonal matrix. All the diagonal entries are 1. So the determinant is just 1. So what does that tell us? Well, this tells us that the determinant of A inverse is 1 over the determinant of A. So, that in and of itself is a really interesting fact. If A has an inverse, then the determinant of A inverse is just 1 over the determinant of A. That's kind of neat. Right? In fact, we can even call that a theorem. the theorem, right? How should we say it? So we should say if A is invertible, then this is true, right? But there's a very important corollary of this. Right? Which is if A is invertible, then something very important has to be true. What do you think? What do you think? What does this equation tell us? That if A is invertible, what has to be true? Well, this right side here is a fraction, and it has the determinant of A in the denominator. So every matrix has a determinant, a well-defined determinant that gives us a number. So if this expression over here on the left is to make sense, then this expression on the right has to make sense. So the determinant of A has to equal 0. Now, we can actually say something even more than that. We can say something stronger than this. Okay, so another theorem here. All right. This theorem we can say is that a square matrix A is invertible if and only if the determinant of A is not 0. Oops, that was supposed to be a not equal to 0 up there. All right. So this basically allows us a trick here. We can check if if a matrix is invertible by checking its determinant. If the determinant is 0, it's not invertible. If the determinant is not 0, then it is invertible. I think I said that right. Again, a determinant of 0 means that it's not invertible. A determinant that's anything other than 0 means it is invertible. All right. So I'll let you think about how the backwards direction of this proof goes. All right. What we wrote up here and this corollary kind of shows us that forward direction. If it's invertible, the determinant's not 0. How about the other way? If the determinant's not 0, then it has to be invertible. How do you show that? I'll let you think about that one. And I'll end this video here because we've kind of gone on for a little bit. But we'll see you for the next one.